Welcome to example number 13. We have a ball rolling down an inclined plane. So we're going to first start off by drawing a free body diagram for the ball. So I'll just maybe draw that over here. We'll call that part A. And we're going to draw a bowling ball like here. Okay. And then probably some inclined surface here. And then now what we need to do is draw forces acting on the bowling ball. So we'll start off maybe with the force right in the middle, we know is the force of gravity. We will label that as F sub G. Okay, what other forces do we have acting on the ball? We have the normal force. Okay, and that we will draw with maybe a slightly different color, maybe black. Okay, and we know that it acts essentially perpendicular to the surface. Okay, so that's our normal force, which I'll just try to shift it right so it's touching the ground right there. And then we have also a frictional force. Now this one people tend to mess up a little bit, but if you think of it, it is accelerating essentially this way. Angularly, right? It's slowing down on the way up the incline, or it's speeding up. In order for it to slow down, rotationally speaking, if it was spinning uphill like this, it would be getting slower and slower rotationally, so we have to have an acceleration that is in the counterclockwise direction. To produce a torque that is going that direction, we need a frictional force that is essentially going to cause a torque that goes counterclockwise, right? So it's something like that, right? Parallel to the surface, but actually up the inclined plane, all right? So we're going to draw that right along the surface right there. Okay, so now we'll just label these forces. This one we will call the force of friction, okay? And then we have this guy over here, we have the normal force. Okay, so those are your forces that are acting at the points where they act. So we're not drawing them from the center, we're drawing them at the positions where they're acting. Okay, so now that we got the free body diagram correct, okay, which is very important, we can now proceed to determine the acceleration. Okay, so a couple of ways that you can do it, and I'll show you two different ways of doing this. So we'll first start off with a typical way, which is basically picking the center mass as you're doing your torques about. So you can do the sum of the torques about the center mass equals I times alpha, right? And then about that center mass, we would not have to worry about the force of gravity because that would be acting at the center mass, so that would produce no torque, but we would have one from the frictional force, right? So we have force of friction multiplied by r and multiplied by sine theta. The normal force would produce no torque because Fn is essentially going straight up along here, and then the r would be going in the exact opposite direction this way, which would produce a sine of 180 degrees. And if you recall, the sine of 180 degrees is 0, so the normal force will produce no torque. So there's no torque produced by the normal force, there's no torque produced by the force of gravity. The only torque we have to worry about is the frictional torque. And then that's equal to I alpha. Okay, and we can make some replacements in here. So maybe we'll just write this as FF for now. We'll figure out what that is. By the way, that angle is not theta. I guess we could just replace that with essentially 90 degrees, which is 1. Okay, and then now we're going to replace the rotational inertia and also the angular acceleration. If you recall, angular acceleration we can replace with A over R, and then we need to find the rotational inertia of a solid ball. So let's go back to our notes in the chart where we have the rotational inertias. Okay, and we are looking at this guy, a solid sphere, which is 2/5 mr squared. So we're going to replace I with 2/5 mr squared. And we should see some cancellations. We can see one of these r's cancel with that r, and that remaining r cancel with that r. So then we end up with the force of friction is equal to 2/5 ma. Okay, so we need to get an expression that has a force of friction, another one, right? And so if you can imagine that this bowling ball is accelerating down the incline, right? That direction, right? So we're going to apply now some of the forces along the x-axis equals ma. So we're choosing an axis that's parallel to the axis down the incline, and y is perpendicular to that plane. So the only, well, let's look at it. What do we have for forces? We have the x component of gravity, right? And then we have the friction. But normal force would be going perpendicular to that. So we really have just Fgx minus the force of friction equals ma, right? And then if we want to write Fgx in terms of components, that's the same thing as writing Fg times sine theta minus force of friction equals ma. And then we replace Fg with mg sine theta minus ff equals ma. Okay, so we have two expressions. We have equation 1 here and equation 2. And we're trying to get an expression for acceleration, so we're going to sub in number 1 into this equation. So we have mg sine theta minus, let's replace ff with 2/5 ma equals ma. Okay, so then we have, going to bring over this negative 2/5 ma to the other side. So that will give you 7/5, right? 7/5 ma equals mg sine theta, right? 5/5 plus 2/5 is 7/5. The m's cancel out, and we get a equals 5/7 g sine theta, and that's the acceleration of the bowling ball down the incline. Now, you might be thinking, maybe there's another way of doing this, right? Maybe there's a faster way, and if you have looked ahead after we talked to class about the parallel axes theorem, you might find it a little bit easier to do it a different way. So I'm just going to show you an alternate solution. So suppose that you did a sum of torques about the point where it makes contact with the ground. We'll call that point P here. Right here where the friction is acting and the normal force is acting. So we'll take sum of torques about point P. That's going to be equal to I alpha, but it's going to be the new I, I'll call I prime times alpha. Right, the reason why that might be easier is that I only have to worry about one force. I don't have to worry about the normal force, nor do I have to worry about the friction force, because both those forces are acting at point P and the distance r is 0. So the only force I have to worry about is basically Fg, right? And that's the only one that's acting away from that point P. So our only torque we have is Fg multiplied by r multiplied by sine theta. And we can work it out and hopefully realize that this is angle theta. So there's r, there's Fg, and there's theta. And that's equal to I prime times alpha, and this is where we use the parallel axes theorem. We have I center mass plus md squared times alpha. Okay, we'll fill this out in a minute here. We'll replace Fg with mg r sine theta equals. Now the I for the center mass is what we had earlier. It would be 2/5 mr squared plus the mass of the bowling ball plus the distance that it's away, and that's just r away. So it's really just adding r squared here times alpha, by the way, which is a over r. So we have mgr sine theta equals, this is going to be 7/5 mr squared times a times over r. And we should see that the r's all cancel out. In fact, the m's as well cancel out. And we get this nice answer of A equals 5/7 g sine theta. And you might find that a little bit faster than the other solution that I did. But there are some things that we may need, because if we look to the next part, we were just doing part B. Okay, if we go to part C, we ask for the frictional force, and we want to write the frictional force in terms of the given variables, which are like m and r and g. All right, so how can we write the frictional force? So part C, we have the frictional force can be written a couple ways. You could either use just FF equals 2/5 MA, or you can use this expression. This one looks simpler, so I'll just write FF equals 2/5 MA. Okay, and then we can replace A with 5/7 g sine theta. So our force of friction, the 5's will cancel out, is equal to 2/5. No, not 2/5, sorry. 2/7, right? 2/7 g sine theta. All right, that's the answer for C. Okay, and then we have part D, which is what is the minimum coefficient of static friction. Okay, so part D, if you recall, FF static for the peak value is mu sub s times Fn. So we've figured out FF, that's 2/7 g sine theta. And Fn, right, what is that? Now let's do that over here on the side. Some of the forces vertically have to add up to 0. So we go back to our free body diagram up here. The normal force must be canceling out with the y component of Fg, right? So Fn minus Fgy equals 0. So Fn equals Fgy, which is basically mg times cosine theta. So we're going to replace that into here. We're going to have mg cosine theta. I see I forgot something. There's an error. See, I realized that m should have canceled. So somehow I'm missing an m in here, right? That came over here, and so there should be an m in there as well. Didn't realize that until now. Anyhow, still, we're okay. Cancel that m's now. Okay, and we can also cancel out the g's as well, right? And we just get basically mu sub s is equal to 2/7 sine theta over cosine theta, which is the same thing as 2/7 times tan theta. Okay, that's part D. And I was just looking through my answer key here down below, and I actually realized I have a typo here. This is incorrect in here. It is not that answer. Mu sub s is, as I've derived it here, 2/7 tan theta. Okay, hope you understood all this. All right, if you have any questions, see me in class.